Ramanujan for G is now available on the Google Play Store. Try it out for free.
Good morning, students. So today we are going to study the relation between the standard cell potential and the free energy change, and also the cell potential and the equilibrium constant. So, but before going into that, let us first understand the Faraday's constant, because it is important for us to understand what is this and from where it comes, what is its value, because everywhere we will be using this F, this term F or the symbol F, and which means this much charge per mole, this Coulomb charge. So the charge, what is the Faraday's constant, is a charge on 1 mole of electrons. And 1 mole of electrons, what we know, that 1 mole of any elementary particle, it means the number of that particle is equal to the Avogadro number. And 1 mole of electron means therefore is Avogadro number of electrons. And what we know, 1 electron has minus this much charge, which is with the negative. So if we just take magnitude, then we do not have to show that much charge, because this Faraday's constant, this could be the charge of not only electron, it could be sometimes people represent for the positive charge as well. So usually this Faraday's constant is this magnitude, its value that we consider the magnitude of the charge on 1 mole of electron. And so it means 1 electron has charge, what is, it is equal to 1.602 into 10 to the power minus 19 Coulomb, and this charge is per electron. We usually should write -1 minus with this before this, because the charge on electron is the negative charge, but we are not showing because we are considering only the magnitude, only the amount of charge that is there, not its sign. And 1 mole, that we know, a 1 mole of electron is what? 1 mole of electron is the Avogadro number of electrons. Avogadro number of electrons is 6.022 into 10 to the power 23 electrons. And this we call per mole, because in 1 mole, this many electrons will be there. And this much charge will be for the 1 electron. So the total charge on Avogadro number of electrons will be the Avogadro number into the charge on 1 electron. And this is what we have written here. And it means the 6.02 into 1.602 into 10 to the power 4, which will be around 9.648 into 10 to the power 4 Coulomb per mole. Coulomb per mole, sometimes it in some books and somewhere, sometimes you may need to understand this. Coulomb is what? Coulomb is joule per volt, because if we know the volt defined as the joule energy per Coulomb, the test charge, when a test charge is brought into an electric field, and the work done is bringing that charge is what? The volt or the potential. And so the potential will be what? Work done divided by the charge, and work done is joule divided by charge Coulomb, the unit. So joule per Coulomb is the volt, and so the Coulomb will be joule per volt. So similarly, so one can write Coulomb by joule per volt, and mole will be there. So the same thing will be there, 9.6048 into 10 to the power 4 joule per volt per mole. And this is what one can write. So Faraday's constant will be 96480 Coulomb per mole. Though this is not exactly same, it depends on this value slightly. You will see different. Somewhere it is reported 487 Coulomb per mole, somewhere 485 Coulomb per mole. So this is what it, depending on the what, up to what place of the decimal you are taking this Avogadro number, or even the amount of the charge on an electron. So depending on this value, what we have taken, the nearest value that one can find easy to remember is 96480 Coulomb per mole. Many books, it also reports that this is 96500 Kelvin per mole, because this 480 is around equals to 500. So many often times, because this number is easy to remember, so people, our students, remember this. And even if you remember this value, you will lead to almost the same result. Slight difference might be there in the decimal points, but you will get the right options when it is there, or even with this value you will get the full marks. So the Faraday's constant, if you can remember this value of 487 or 485, whatever the your book suggests. But what I see, if that is difficult for you to remember, you can remember this value. So the F is what? 96480 Coulomb per mole, or this is approximately equal to 96500, 96,500 Coulomb per mole. This is the Faraday's constant. This is what? This is the charge of 1 mole of electrons, the magnitude of charge of 1 mole of electrons. If the exact charge I have to calculate on 1 mole of electrons, so it will be with the minus sign, minus 96480 coulomb per mole. This thing you should remember. Now let us look into the relationship between E naught and delta G. What is E naught? It is a standard cell potential, and delta G naught, it is a standard free energy change. So there is a relation, there exists between E naught and delta G, and we can get this value and delta G because we know the definition of the delta G, the free energy. And from the free energy, and we also don't know what is the nature of this E naught. And based on that, we can find out a relationship between them. So what we know, N the work done, the free energy change is what? The energy available to do perform work. And this energy, the whole energy if you use in performing work, that will be in the standard state. So that energy you can do, and that energy is what? Any electrical work done is what? If a charge is transferred from one place to another place along a potential difference, or maybe if the Q charge is transferred in a potential difference of V delta V, so the work done is equal to Q into delta V. This is what we know from the we know from the this physics class. So what we know that in this case, so this potential difference in the standard state is what? E naught. It is a cell potential, and the potential difference between the two electrodes and under the standard state means that if all the quantities they are in the under the standard state, if it the means the concentration of all the electrolytes should be 1 molar. If there is any gas involved, at the pressure of that gas should be 1 atmospheric pressure, and the temperature should be around 25 degrees or exactly 25 degrees. So those are the standard states. So the standard free energy change of a process delta, which is delta G naught, is defined as the maximum work that could be performed by a system, and that one can represent as W max. And in the case of a redox reaction taking place within a galvanic cell that we know, or the voltaic cell, we also call it. So under a standard state conditions, essentially, and all the work is associated with the transferring the electrons from the reductant to oxidant, and thus we can represent this work is W electric. So what we know, this I have also explained earlier. So delta G, whatever the free energy change that is there, so what can we do? We can use this energy in transferring electrons from one electrode to another electrode. And that energy, once the electron is transferred, so what we say, electron is moving, it is going in certain directions. So what can we do? We can extract electricity. We can see electricity is being produced there, and that electricity one can use in different running certain appliances, the electric bulb, fan, geyser, anything that you want to. So in the case of redox reactions taking place within a galvanic cell under standard conditions, essentially all the work is associated with transferring electrons from reductant to oxidant. So what it means, the reductant where the reduction is happening and the oxidation is going on. So the delta G naught we can write as W max. The maximum work can be performed under the standard state, and which will be equal to the what? The W electric means the same energy or this work will be done in transferring electron along a potential difference, and that potential difference is nothing but the difference between the potential of the two electrodes, the cathode and anode. The work associated with transferring electron is determined by total amount of charge transfer and the cell potential. This is what we, in this case, what one can do. Usually any charge, when it is transferred along a potential, means it has moved from one potential to another potential. The work that we know, work done, is equal to the amount of charge into the potential difference. So this is in the case, this will be the cell potential and the amount of charge being transferred. If the 1 mole of, whether it is 1 mole of charge is being transferred or n mole of the charge will be transferred. 1 mole of charge means 1 mole of electron, because electrons are being transferred here, electrons move there. So the total charge transferred in the form of electrons, that we can calculate as number of moles of electrons. Suppose it is a redox reaction which is happening in a electrochemical cell where the only 1 electron is involved in that reaction. So that will what? Only 1 Faraday of the charge will be moving. And suppose in the case of Daniel cell, we have seen 2 electrons are involved, like zinc ion gets converted into zinc 2 plus, and it loses 2 electrons, and now these 2 electrons per atom are produced, and they move to the cathode, and there these 2 electrons are used by the copper 2 plus ion, cupric ion. So what does it means? The 2 electron per atom means the 2 mole of electrons per mole of atom. So what can we do? The electrons, the total number of electrons thus transferred will be the number of moles of electrons into the Faraday's constant. This F is what? It is the electrons. And in the case of electrons, if you want to calculate charge, we can write, because this charge, as I explained earlier, it is minus F charge. So this is minus NF. The net charge, if I have to calculate, is minus NF charge, where N is the number of moles of electrons transferred from the balanced oxidation reduction reaction that we know and have explained. So N number of, in the case of Daniell cell, it is 1. If the Ag ion will be involved, and suppose Ag ion is involved and another reaction where also only 1 electron is being produced or accepted, what we will see that in that reaction only 1 electron is being used. And suppose a reaction is involving the ferric ion. The ferric ion is reduced into, suppose in that reaction, to the ferrous atom, to the iron atom, Fe atom, then the 3 electrons will be involved in that reaction. So in that case, this value of N will be 3. So that NF will be minus 3F. And why the moles that we are considering here? Because if we know in chemistry amount of any measurable quantity that we measure, that we always represent it in the terms of the mole. Because in chemistry we quantify all the measurable quantities per mole of a substance, because we know from the SI unit that the mole of amount of any substance is represented in terms of the mole. And mole is, that is the why it is the fundamental unit. So in chemistry, we represent everything in the terms of mole. So even for electrons, we measure it in terms of the per mole electron transfer, and so that is why we came with the Faraday's constant. So now the total charge transfer will be minus NF, the net charge minus NF. And so from this equation again, we can write delta G naught is equal to W electric, and delta G naught is equal to W electric will be what? Charge into the coulombs that we know, into the potential difference. And potential difference here is what? The maximum potential difference is what? The standard cell potential. So what is the charge in coulombs will be what? Minus NF, because this F is also coulomb per mole. So this will be, charge in coulomb will be minus NF, and this potential difference is E naught cell, because E naught cell is the maximum potential the cell can produce, and that maximum potential is related to the maximum work that can be performed. So now we can write delta G naught is equal to minus NF E naught cell. So this is the equation, this is the relation between delta G naught and E naught cell. So this relation, now we have obtained the relation between E naught and delta G. This relation is very important. And what you know here is the delta G. Delta G is negative. If the E naught cell is positive, then this F is a positive. As we know, this positive constant, because this minus comes because of the electron, a negative charge. But F, the constant is what we, whenever value of F we have to put, we put this value. So this value we put, F is a constant, N is the number of electrons, which will always be positive. So N is positive, F is positive, and if E naught cell is positive, so what will we get? Delta G naught will be negative, and delta G naught is negative, means less than 0, means the reaction will be spontaneous. And if E naught cell is negative, then this entire thing will be positive, and delta G naught will be positive. In such case, the reaction will be non-spontaneous. And that is what we know. So the relation of how this E naught cell, positive E naught cell, is related to the spontaneity of that certain reaction is now we can see from this relation. And we have seen in our last class, we somehow tried to correlate it. And here we get this information very clearly. The relation between the free energy change and the standard cell potential conforms the sign convention and spontaneity criteria. What is this criteria? Spontaneous redox reactions exhibit positive potentials and negative free energy changes. Let us look into this question. The standard electrode potential for Daniell cell, and this will be based on this formula. So the standard electrode potential for Daniell cell is 1.1 volt. Calculate sometimes what can be given, that reactions will be given. E naught means reduction potential for the zinc electrode and copper electrode will be given. From there you can find out the electrode potential of that cell Daniell cell, and then you can do the same thing. So anyway, that this value in this case is directly given. So a standard cell potential for the entire cell is given, not for one electrode, the entire cell is given. Calculate the standard Gibbs energy for the reaction. And this is the reaction, zinc solid, it gives it reacts with CO2 plus, the net reaction, and 2 electrons will be involved in this case, and it gives zinc 2 plus aqueous plus Cu solid. So what we know from this question is E naught cell is given, it is 1.1 volt. And if it was not given, as I said, you could have calculated it from the standard reduction potential of the zinc electrode and the copper electrode separately. And from that, you can have 0.76, and for the copper, we know 0.34 if you add. So you will get the same value. So the solution, now the E naught cell is known, the standard free energy change we can calculate for this reaction, and that will be delta G naught will be equal to minus Fe naught cell. And we know in this case how many electrons are involved. 2 electrons are involved because 2 plus charge is there. So the 2 electrons were released when zinc is converted into zinc 2 plus, and the same those 2 electrons will be taken away, accepted or received by the copper 2 plus ion. So 2 electrons are involved in this reaction. So the N value of N will be 2. F is what? Faraday's constant that I have written here, taken as a 96,500 coulomb per mole, and into the cell potential E naught cell for the Daniell cell is 1.1 volt that is given. So this will be the value 212300 joule per mole, and this joule per mole we can convert into the kilojoule per mole. So we have divided this number by 1000. So this will be 212.3 kilojoule per mole. This is our answer. Now let us look into the how can we get the relationship between E naught and K. What is the relationship between E naught? E naught is what? A standard cell potential, and K is the equilibrium constant. Because the cell reaction can also reach to the equilibrium after a certain time. So this is what we know. Once the equilibrium is released, what will from which how will we calculate E naught cell or something like that? So to do that, let us remember the relation of the expression that we have studied in the thermodynamics. What we have studied there, delta G naught is equal to minus RT ln K. And usually what we have this equation is delta G for not in standard condition is equal to delta G naught plus RT ln K, where delta G naught is the free energy change in the standard condition, and delta G at energy, and ln K, not ln K, there we write ln Q, and the Q is the reaction quotient. And means and this reaction quotient, if you remember, it contains the concentration of products and reactants at any time, not only at the equilibrium. And when those react concentration belongs to the equilibrium concentration, Q becomes K, the equilibrium constant. And what we know that once the reaction reaches to the equilibrium, this Q becomes equals to K, and also delta G, it becomes equal to 0. So 0 will be equal to delta G naught plus RT ln K, and so delta G naught is equal to minus RT ln K, and this equation that we get from the thermodynamics, and I have written it directly here. And you can look into that chapter on the thermodynamics. So delta G naught is now is equal to minus RT ln K, we know, and delta G naught is equal to minus NF E naught cell. We have just seen, we have just derived this equation. So we can just equate these two right hand side things. So right hand side portions it will equate. So minus RT ln K will be equal to K is equilibrium constant. You should remember it's a K, capital K is equilibrium constant. R is universal gas constant. T is the temperature that we know, and this is equal to minus NF E naught cell from here. So now I can write E naught cell is equal to minus sign will be cancelled out. So it will be equal to RT by NF ln K. And what we know, the ln K, if you convert ln K, which is the base E, if you convert it into the base 10, so we have to multiply this thing log base, the same thing with the 2.303. So ln K will be equal to 2.303 log base 10 K. Log K on base 10. So 2.303 I have written before this RT. So the same thing will be E naught cell will be equal to 2.303 RT by NF log K. Or even if you remember this equation, that is okay. Then you have to take the log value in terms of the base E, not base 10. So this equation indicates redox reactions with large positive standard cell potential. What does it mean? This large positive E naught cell standard cell potential will be there. Proceed forward to towards the completion. Again, I will repeat it. This equation E naught cell is equal to RT by NF ln K, indicates redox reactions with large positive standard potential, means this positive standard potential E0 cell will proceed forward towards completion. So it will reach to completion because how? Because E0 cell, if this is positive, so ln K will be E0 cell into NF divided by RT, and this value is positive. So e to the power certain positive value, once you remove the long, so it will e to the power certain positive number, and that we know we will get certain value which will be quite high. So if E naught cell will be very high, because again here the F is the Faraday's constant value is already high, 96500. N is, if is not going to be less than 1, it will be 1, 2 or anything, and RT it is simply 8.13. So what we get this value, so definitely NF by RT is certain positive number. If E naught cell is more than 1 or more higher value, then we will get this value of log K will be too high or the K will be very high. It means the reaction is towards the completion, or it is near to the completion, and so reaching equilibrium when the majority of reactant has been already converted to the product. So the reaction will reach the equilibrium, cell reaction will reach the equilibrium when majority of the reactants will reach towards the completion or reach towards the formation of the product. So now these three things that we can put on the different three vertices of a triangle. So the K, equilibrium constant, E naught cell that we know the standard cell potential, and delta G naught is the standard free energy change, and the relation between this delta G naught and E naught cell is delta G naught is equal to minus NFE, and the relationship between delta G naught and K is what? Delta G naught is equal to minus RT ln K, and K and E naught cell, we know E naught cell is equal to RT, this equation, divided by NF ln K. So this equation is very important, and from this equation one can also look at this table. The K, when K is more than 1, if you look at the equilibrium constant, and if the equilibrium constant is more than 1, what does it mean? If the equilibrium constant is more than 1, then in this equation, if you look at the, this is more than 1, it means this value will be more than 0, so some positive value we will get for this RT ln K, and the positive value we get means the delta G will be negative, and the delta G will be negative means ln K will be positive if the K is more than 0. The ln K will be positive, so the RT ln K will also be a positive number. So delta G naught, which is equal to minus RT ln K, will be a negative number, a negative value, and negative value means the reaction will be spontaneous under a standard condition, and the product is more abundant at the equilibrium, and we will see the product is more abundant at the equilibrium. The similar thing we can see, delta G is less than 0 means the negative is less than 0. So E naught cell will be positive, because we can, same thing we can put here, delta G naught is negative, less than 0, and negative will be cancelled out. So E naught cell will be a positive number. So the E naught cell will be greater than 0. And if K is less than 1, and if K is less than 1, that we know, if the K is 1, then log 1 is 0. So if the K is 1, we can calculate the log K will be, log 1 will be 0. So log K will be 0 if K is 1. In that case, the delta G will be 0. Delta G naught will be, in that case, will be 0. E naught cell will also be 0. Means the reaction is already at equilibrium. However, if the K is less than 1, if the K is less than 1, we get the log value is negative, because log value is defined more than 0, for numbers for more than 0, positive numbers only, and the values, but for the log K value for any number between 0 and 1, the log value for those numbers comes into the negative. So log K, if the K is less than 1, then log K will be negative, and log K will be negative means and delta G will be positive, because it is minus RT log K. So delta G will be positive. Delta G is positive means that delta G is greater than 0, and delta G is greater than 0, that we know the reaction is non-spontaneous under standard conditions. So reaction will be non-spontaneous, and a reactant non-spontaneous, in that case will be reactant more abundant at equilibrium. And what we know that, and if this E naught cell, from that we can also get, if the delta G is what positive, then E naught cell will also be negative, and E naught cell now will be, delta G is positive, the E naught cell will be negative, and E naught cell will be negative, and E naught cell is less than 0. So from this table, we get certain information, and these informations are based on the interpreting these equations that we have seen, these three equations that we have just seen here in this triangle. So these are the relations between three important thermodynamic properties that are important for us to understand in this chapter as well. Let us now take this question, calculate the standard shell potential, standard free energy change, and the equilibrium constant for the following reactions at 25 degrees centigrade. The comment on the 25 degrees centigrade means we know that is the standard conditions. And one thing just I forgot to mention you here is if we are talking about E naught cell, we are talking about delta G naught means the standard condition we are talking about. Once we are talking about the standard condition, then this T will already be 25 degrees centigrade. And the value of R is that we know 25 degrees centigrade means 298 Kelvin. And the value of R we know 8.314 joule per Kelvin per mole, and value of F we know the N. So what can we get? The R value of R, T, and F we can put, and putting these values, what we get, it comes to be 0.0592, and that its unit will be volt divided by N. And the RT by F, if you put the units of all these quantities, you will get this unit will also be volt, and that should actually be, because log K will be unitless because it's a number. So log K will be a number, it's unitless, and E naught cell, its unit is volt. So this is volt and this is unitless, means this quantity, entire quantity's unit should be volt, or the dimensions will be volt, and volt means number. N is also the number of electrons. It is a dimensionless quantity. So RT by F should be should have an unit equals to volt. So this is what one can understand from there as well. So now let us look into solving this question. So the standard, the temperature is already given, and this is the reaction. 2Ag plus aqueous gives Fe, reacts with Fe solid, gives 2Ag solid plus Fe2 plus. Here we know which reaction is the oxidation reaction. Fe gives Fe2 plus, the Fe is being oxidized, and these 2 electrons are being used by 2Ag plus and to reduce it to silver, solid or silver atom. And here also, once the iron is, we know iron is being oxidized, means iron forms the anode. This we know because at anode, in a Deliel cell, oxidation happens. So anodic reaction or the oxidation, we can write what is the oxidation reaction here. Fe solid 2 plus aqueous plus 2 electrons we can write, because to balance this plus 2 electron, and for E naught, this reduction potential for this reaction is already reduction potential for this reaction is already given. Please note that this is the oxidation reaction. However, the potential for this reaction is given in the opposite direction. This is for the reduction, means if Fe2 plus accepts 2 electron to give Fe, what would be the cell potential? That is negative, because Fe2 plus do not like to accept electrons, it likes to give electrons. So in this direction the value will be positive. In the opposite direction, this direction, which is the reduction reaction, the value is negative. So this value is negative, it is given already, it is provided. And the cathode reaction will be what? It is the reduction reaction. And what is the reduction? It is Ag plus giving Ag solid. So Ag plus, so it will react with 1 electron, it will accept 1 electron to give Ag solid. But what we know, the 2 electrons are being removed from per atom of the iron. So we need 2 Ag plus ions to accept, to consume these 2 electrons. So for 2 moles, we need 2 moles of Ag2 plus. So we have to multiply this entire reaction with 2. So 2 into this. So and this, for this reaction, E naught Ag plus this reduction potential for this standard reduction potential for this reaction is given as 0.8 volt, 0.80 volt. From here we can get the E shell, or E shell or E naught cell will be E naught cathode minus E naught anode. We have seen, we have derived this thing as well, and this E naught, but this in the reduction form we will be taking only. So E naught cell means the standard reduction potential for this, the reaction happening at cathode and for at anode as well. So this will be, what is that? The cathode is the Ag, silver electrode is there. So for silver electrode, the reduction standard reduction potential will be writing here the 0.8 volt minus the standard reduction potential at the anode and electrode, which is at the anode, and this is the iron electrode. So we will write this uh, standard reduction potential for the iron electrode, and that iron electrode, this value is the standard reduction potential is minus 0.44 volt. So this minus is here and this minus is from here, so that we write, and that this minus minus will be plus, it will be coming to the net value will be plus 1.24 volt. So from here we have to, what is comments on the spontaneity of the forward reaction. So what can we can predict, since E not cell is positive, so we can predict here from it here itself that this reaction in the forward direction will be spontaneous. But we have to also calculate the equilibrium constant and the free energy change. The standard free energy change we can also calculate. Let us first calculate the equilibrium constant. The equilibrium constant will be RT divided by NF ln K. So RT, we know the value of R and T, as I said, divided by F is equal to 0.0592 volt. N value of N, we write it is equal to 2 because 2 electrons are involved in this reaction. So 2 for 1 mole of iron atom, 2 moles of electrons will be involved. So that this value will be, value of N is 2. So RT by F is equal to 0.0592. You can put the value of R 8.314, T value is 298 Kelvin. So you can put 298 Kelvin divided by this value F 96500, and you will get this value will be close to 0.0592 volt divided by N, and value of N is 2 in this case, for this case. The 2 and the ln K that we write here. It means what this means, that K will be equal to, or anyway from here directly we can also write this thing. So the K will be equal to this E naught cell into 2, because this thing you can, E naught cell value we have just calculated, it is 1.24 volt. So E naught cell one can write is, this is equal to, so this equation is already given. E naught cell value we have written 1.24 volt, and this RT ln by NF ln K will be coming to this. So from here ln K will be 1.24 volt. This volt will be cancelled out. So ln K will be equal to 1.24 into 2 divided by 0.0592. So the K will be equal to, because ln K is base E, so K will be equal to E to the power this value, so E to the power 1.24 into 2 divided by 0.0592. This is equal to E to the power minus 40, E to the power 41.89. After solving this, we will get 41.89. And then getting the value, the exponential value we get, this is 1.56 into 10 to the power 18. And here you can see the value of equilibrium constant is too high. It means the reaction is almost near the completion. So at the equilibrium, reaction is almost near the completion in this case. Now that we can also calculate the standard free energy change. A standard free energy change we can calculate from del E naught cell again. E naught cell is given here. So delta G naught is equal to minus F E naught cell. Minus N. N is what? Minus, and N is 2. F is 96500 coulomb per mole, that we have, we know. This value we have obtained, Faradays constant, and into 1.24 is what? E naught cell for this reaction, and 1.24 joule per coulomb, and this value is what? With the negative sign, 239,320 joule per mole, and we can convert this joule per mole to kilojoule per mole. To do that, we have to divide this number by 1000. So we divide this number by 1000, so it will be coming to minus 239.32, because we have to put the decimal point here. So 239.32 kilojoule per mole. This is the value of delta G. Now again, what we get, the delta G value of delta G is negative, and the value of delta G is negative means the reaction is spontaneous, as indicated by the as indicated also by the positive cell potential or the free energy. And the value of K is very large, that we see here, because we have to see what does it mean. The value of K is very large. It means what? It indicates that the reaction proceeds to near completion to yield an equilibrium mixture containing mostly the products. So reaction mixture at equilibrium will mostly contains products, because the equilibrium constant is very high. It means that even if you remember this equilibrium constant value in terms of the concentration, so product concentration is too high than the reactant concentration. That is why value of K is very high. Now let us look at this. What we have seen the potential at the standard condition. But the thing is, when we draw the energy from the cell, and but we see that concentration is changing with the time. Concentration, electrode concentration will also be, the electrode concentration at the different electrodes will be changing. And not only the most redox processes that also science interest science and the society do not occur under a standard conditions. They do not occur always in standard conditions, because we know the temperature is not 25 degrees natural temperature at different places. The temperature will be different at different places. So that temperature we have considered 25 degree, but in reality these conditions are standard conditions are not there. Even the pressure sometimes it changes, the atmospheric pressure and other things. And the concentration is also it can be changed during the course of reaction. So the most of the redox processes that interest science and society do not occur under standard state conditions, and show the potential of these systems under non-standard conditions are a property worthy of attention. Because of course we can measure these things from at the standard conditions. We have equations that we have derived, and from that we can calculate. But the thing is, we need certain relations so that we can calculate the cell potential even at the non-standard conditions, because the non-standard condition is the most viable condition practically. So we should have certain relations, certain idea that how will we calculate the cell potential at the non-standard condition. So for example, for these problems that you know, while using a battery, you might have observed that its power decrease just during the discharge cycle. So why do you see so? Why do you need to recharge a battery? What happens during recharging? So why do we do in recharging? Why recharging happens after the recharge? Once you start taking battery, and after a certain time you will see, before this battery is completely discharged, mostly in the fan and any appliances you are running, you will see its speed will go down. So this happens. Why this is so? So during the discharge, what we know, during discharge, electrolyte concentration at electrodes changes because of the cell reactions. And that's because cell reactions are happening, so electrolyte concentration will also be changing. And thus, although we try to make this electrolyte concentration constant, because we try somehow to add these electrolytes from the this salt bridges, but this is do not compensate the everything, all the lapses. So although it's increases, adding of the salt bridges increases the efficiency of these cells. Anyway, during the discharge, electrolyte concentration and electrodes changes because of the cell reactions. Thus, the measured electrode potential is not a constant quantity. It depends slightly on the concentration of these ions that is there. Although you add certain ions from the this salt bridge, but those ions are not the same ion that are taking part in this cell reaction. They are different ions. So these different ions, so their concentration will not be affecting the equilibrium constant of the cell reaction of this particular cell reaction. So the relation between what we get, relation between energy change and the reaction mixture composition, that we know from the thermodynamics. This equation we have read. I have just a few minutes ago I have explained it. So this equation at the non-standard condition, what we get, delta G is equal to delta G naught plus RT ln K. And ln Q. Q is what? The reaction quotient. This reaction quotient represents the concentration of products and reactants at any time. It need not necessarily be the equilibrium concentration or the equilibrium condition, but this Q, once this Q, the concentration of these reactants and products become equal to the equilibrium concentration, then this Q becomes K, as I have said, and the Q becomes K, means then the delta G naught, G becomes 0 at equilibrium. And that is how we get the equation delta G naught is equal to R minus RT ln K. In this equation, what we know, as we know, delta G naught is equal to minus NF E naught. Similarly, we can find out the relation for the delta G as well. If the E naught, the delta G naught is what at the standard condition, free energy change. So this is the E naught cell that we have written, the standard electrode potential, standard cell potential. But if the cell potential is not E naught cell, suppose it is E cell, then the delta free energy change will be not the free energy change at the standard condition. It will be equals to the non-standard free energy change at a non-standard condition. So there we can write delta G is equal to minus NFE or NFE shell. So you can write delta G as minus NFE shell and delta G naught as equal to minus NFE naught shell, and this plus RT ln K we can write here. And this what we know, the reaction coefficient Q appears in this equation makes the free energy change dependent upon the composition of the reaction mixture, and that we know this reaction mixture Q is related to the concentration of the reaction mixture, and that is how we see the free energy change is related to this, because RT ln Q will have certain value, and based on that this value of G will be delta G will be depending, because delta G naught we can consider a constant in this case. So based on this value RT ln Q, this value of delta G will be changing. And substituting the equation relating free energy change to cell potential yields Nernst equation. This is the Nernst equation that we get, the minus NFE ln K. And if you divide this entire equation by NF or minus NF, so if I divide minus NF the both side of this reaction, so this will be minus NF E cell divided by minus NF. So minus NF minus NF will be cancelled out. So this E cell will be left off. Now here in this case, it will become minus NF E naught cell divided by minus NF, or minus NF again will be cancelled out. So it will become plus E naught cell. And this is RT ln Q divided by minus NF, and minus NF, this will make minus, and this plus make this term minus, and it will become minus RT by NF ln Q. And so we get this Nernst equation, the E shell is equal to E naught cell minus RT divided by NF ln Q. This is the Nernst equation that we know. This is a very famous equation, and using this equation you can calculate the cell potential at non-standard condition at any constant condition. And here what you see, this E cell is now dependent on few things. It depends on the temperature. This T is the temperature. If you change the temperature, E cell will be varying. Now if you change the value N, the number of electrons taking part into the cell reaction, if you change the N, then also E cell will be changing. And if you change the value of ln K, it will also be changed. Why I have not changed it? Doesn't, R is a constant, so it is a constant. F is also a constant. Faraday's constant is also a constant. So the E cell in this, from this Nernst equation, we see that depends on the three things, three parameters, and these parameters are number of electrons taking part in the reaction, the temperature at which the cell reaction is happening, and the reaction coefficient of that cell reaction at that particular instant, that particular time. So the Nernst equation show that the potential, this thing I have already explained. So so this equation describes how the potential of redox reaction, this Nernst equation, such as a galvanic cell varies from its standard state values. So how it will vary from the standard state values, because E is not cell with the standard state values. So depending on this value, this entire values, if the E cell will be there, and by that much value it will be deducted. You should deduct this from this E naught cell. So that's the E cell you will be getting. We can also get how the electrode potential varies with the concentration of electrolyte from the Nernst equation, because we know the concentration of electrolyte is Q. It contains the concentration of product. Concentration of product is, what is the product there? Then they form of the electrolyte, because in the electrolytes reaction is happening. Once the reaction though is happening at the electrode, but with the electrode, what is varying the electrolyte concentration. And electrolyte concentration, the species that is involved there. So for example, that we have seen in the Daniell cell, or even suppose not Daniell cell, let us look at this example. Active, the oxidation is happening. With the each oxidation of each atom, what we are seeing, the iron, the Fe2 plus ion, ferrous ion concentration of ferrous ion is increasing into the electrolyte which is at the anode. And now with each reaction, what we see, the Ag plus ion is consumed, and with that the Ag plus ion concentration is decreasing. So what we know, the concentration of these electrolytes will be decreasing with the time. And so depending on that, one can also understand that the electrode potential will also be varied. And electrode potential, how will we calculate the electrode potential? So for the electrode reactions, suppose this is the electrode reaction, a general electrode reaction. Mn plus aqueous plus n electron is involved, and this is the n plus charge, and this is the m plus. This is the standard reduction potential usually we describe. So the reduction reaction only we have considered here. And the electrode potential, similar to this equation on this term, we can write electrode potential at any concentration measured with respect to a standard hydrogen electrode can be represented, because this we measure with respect to a standard hydrogen electrode only, and that we can do. And this is what the standard, this reduction potential is what the Mn plus by Mn, this belongs to this E cell, which is equal to E naught, this standard reduction potential, and a standard reduction potential for cell is this E naught cell, and minus RT divided by NF ln M, that we know what this is the concentration, this is the product, M divided by concentration of Mn plus ion. And since the why this is solid, and we have seen in the chemical equilibrium that if the reactants and products are solid or liquid, we can consider their concentration equals to unity, because their concentration is not going to change. And why this is not going to change? Because what is the concentration? Concentration is what? Number of moles divided by volume. A number of moles in a particular, what we know, whatever it is there in a given volume, if the number of atoms are changing, accordingly volume will also change, and number of atoms is what it is belongs. This is how we calculate also the number of moles. So anyway, the number of this M, concentration of M, the solid, we can consider as unity, and once this is unity, we can write E Mn plus M for this E cell. For this is for the half cell only. The electrode potential, this is electrode potential at a non-standard condition, is equal to the electrode potential at a standard condition, or the standard reduction potential, minus RT by NF. Again the same equation. N, again that the number of electrons involved, and here the electrons involved is N. So F is Faradays constant, T is the temperature, R is, we know, the gas constant, and this is into ln, and this M I have put value of M as 1, and then concentration of Mn plus. And so let me just this is the concentration. So now have just, so we can see here now that E is what? Again, E is what? E naught cell minus RT ln, for this cell electrode potential as well. So this equation you can just generally, E cell is equal to E naught cell minus RT by NF ln K. The similar thing you can do. However, in the case of half cell, then the ln Q, what the ln Q is what? It is nothing but 1 divided by NF plus, and it the ln Q that we know in this, for this reaction, Q is what? Concentration of product divided by concentration of reactant at the given time, and this, that is what we have taken M capital. You can take this concentration of M divided by concentration of Mn plus, concentration of M is 1. So we get this equation for the at the non-standard condition for the electrode potential as well. So E is equal to E naught minus RT by NF ln 1 by Mn plus. And where R is the gas constant, and its value is 8.314 joule per Kelvin per mole. This unit you should always remember. F is the Faraday's constant. This value is 96,480 coulomb per mole, or you can remember this value close to 96,500 coulomb per mole. And T is the temperature in Kelvin, that we know that usually in the chemistry we consider temperature in Kelvin only. The Mn plus is the concentration of the species Mn plus, of this concentration, this in the square bracket. Mn plus means the concentration of species Mn plus. Now if we can take the example of the Daniell cell, the Daniell cell, what is the Daniell cell? The electrode potential for the Cu and zinc electrode in Daniell cell can be written as, and what the cathode reaction, what we know, the cathode, the reduction reaction, and what is reduced in the Daniell cell, it is copper ion is reduced. So copper ion 2 plus 2 electron gives copper solid, is that reduction reaction, and reduction reaction from this we can write ECU2 plus Cu as per this equation. This equation ECU2 plus Cu, and then E naught Cu2 plus Cu minus RT divided by N, it will be 2 into F ln 1 divided by concentration of Cu2 plus ion, and this is what we get here. And for the anode reaction where the oxidation is happening, so even though the oxidation will be happening, but the thing is that what we represent, this is the only the reduction reaction will represent. Although the anode oxidation happens, but this E naught E cell that we measure is for the reduction reaction. And so the opposite reaction that is written here, the opposite reaction we have written Zn2 plus aqueous plus 2 electron gives Zn, because this is a reduction reaction. Although the oxidation happens here, because we are calculating this E cell in terms of the reduction potential. So E cell Zn2 plus 2 Zn will be equal to E naught Zn2 plus Zn minus RT by 2F ln 1 divided by zinc ion concentration. The only difference between them is what? The zinc ion concentration. This RT by 2F will be the same. Zinc ion concentration for here, zinc electrode, copper ion concentration for the copper electrode, and also E naught. The standard reduction potential for copper electrode will be different, and standard reduction potential for the zinc electrode will be different. These values will be also be different. Now what can we do? We can calculate the cell potential from here. And how we calculate cell potential from the half cell potential is what? We just do the E cathode minus E anode. So E cathode in the terms of reduction potential itself. So at the non-standard conditions, because this is the non-standard condition, so what we do? E cathode minus E anode. So we can write it as the ECU2 plus minus Cu minus E. This is the non-standard condition. The cathode is this reaction minus anode. So ECU2 plus Cu minus E Zn2 plus Zn. And this reaction now we can write, we put the value of E cathode and E anode here. So E cathode is what? E cathode is this E naught Cu2 plus Cu minus RT by 2F ln 1 divided by copper 2 plus ion concentration. So this minus, we can write E anode, and E anode is this value. Or E anode is what? E Zn2 plus zinc. So E Zn2 plus Zn, this value we can put here. We have put these values. So now taking out this terms out of the this parenthesis, and we get this term will be with the minus, and I have put this minus E naught Zn2 plus Zn with this E naught Cu2 plus Cu, and this we can write them together. And now this minus RT divided by 2F ln 1 divided by copper ion concentration, copper 2 plus ion concentration, and this minus will become plus, and this minus plus, then we can write these two terms with the R8 by 2F means the terms with the log, and terms without log we can separate them out. And what we know, E naught Cu2 plus Cu divided by E naught Zn2 plus Zn is what? It is nothing but E naught cell for this Daniell cell, and this is E naught cell, and E naught cell we can write here this E naught cell. So E cell is what? E cell is equal to this E naught cell. So E naught cell minus, then we can take this minus sign here, minus will take the common, so the RT by 2F, and this will be ln, and this 1 by Cu2 plus minus this, and minus we know the log, the minus means the divide thing it comes, and mathematically if you do, you will get the zinc 2 plus ion concentration divided by copper 2 plus ion concentration, and RT by 2F is common. So E cell that what we get, E cell is E naught cell minus RT by 2F ln Zn2 plus by Cu2 plus concentration. And this equation we can, this is again the Nernst equation, and this equation is nothing for the same equation that we have derived here for the Daniell cell. This ln Q is what? The concentration of product minus divided by concentration of reactant. Q is what? Concentration product by concentration of reactant at a given time. And when we write this net equation for this Daniell cell, we have Zn plus Cu2 plus gives Zn2 plus divided by Zn2 plus Cu. Concentration of Cu solid and concentration of zinc solid we can consider as unity. So the concentration of now we will be equal to, the Q will be equal to concentration of zinc plus, which is in the product, and divided by concentration of Cu2 plus, which is in the reactant, and thus we get the Nernst equation. That's this equation. as you know here. Now we can put the ln, if you convert this ln base e log base e to log base 10. So then we have to multiply this term with the 2.303. So 2.303 I have done. RT divided by 2F, this is what we get. And this equation actually with the 2.3 RT divided by F, you know, it is 0.0592 divided by 2. And this log base 10 and then 2 plus divided by this and this E0 cell, that then we can see this RT 2.303 RT divided by F is what? This 0.0592. And this unit we are not writing here, unit not writing for E0 cell as well. Here also we are not writing because E0 cell unit is volt, this cell unit is volt, so this is also volt. And log this value will not be having any unit. We see that the E cell depends on the concentration of both Cu2 plus ion and Zn2 plus ion in this equation. So once the Zn2 plus ion and Cu2 plus ion concentration will change during the cell reaction, and this reaction will happen when you draw energy from the cell, you draw electricity from the cell, and since this concentration are changing, that is why the power, even the voltage of that cell, or means the voltage of that cell or the battery decreases as you once you start taking energy out of it. And that is how we see after a certain time, the slowly and slowly the voltage and the power with which the fan and anything it runs, it decreases. And that we see that the non-standard condition, this value, because of Zn2 plus and Cu plus. In the case of Daniell cell, the similar thing will be there for the any other galvanic cell, or we also call galvanic cell as voltaic cell. So it increases with the increase in the concentration of Cu2 plus ion, and what we also know, the concentration of Cu2 plus ion will be more. Cu2 plus ion means the reactant is more. If it is more, then what will be this log value on the log will be less. Because this value is more, so zinc plus ion concentration divided by this value will be less, and the value will be less than value in terms of log will be the entire value will be less, and entire value will be less, then that value with the multiplication with this will be also be less. Then we have to subtract a smaller number with E0 cell to calculate E cell. So if the concentration of Cu2 plus is more, the voltage that we get, the potential we get from the battery usually or the cell is more. Or if the Zn2 plus ion concentration is more, then we get the opposite thing. And what we know, the Cu2 plus ion concentration is more means the what? The concentration that the battery, that initial concentration is already there at the standard, perhaps near to a standard condition. A zinc 2 plus ion concentration is more means the reaction has gone much forward towards, and much forward means it is about to reach the equilibrium. And zinc 2 plus ion concentration is less means the value of Q, again you can see the value of Q is less, value of Q is smaller, a value of Q is smaller than the equilibrium constant. It means the reaction will proceed into the forward direction. And these things we have seen in the chemical equilibrium, how from the value of Q and the number that you know for the equilibrium constant, you can get whether the reaction will be moving into the forward direction or the reverse direction at a given instant. So we now should use the same number of electrons N for both the electrodes for a general reaction. And so we do this a general reaction. You can write this thing. I have already, I think we do not need to explain this. It is already given there. And this means I have already explained. We get this here. Now let us solve this equation. So this, write the Nernst equation for the following cell reaction. The Nernst equation for this reaction is what? This nickel solid, it's converted to nickel 2. For this reaction, this is the anodic reaction. And anodic, then we move from anode to cathode. So anode nickel 2 plus, sorry, nickel converted into nickel 2 plus. This is the oxidation, and the reduction is this. This is the cathodic reaction. And so the cell reaction is what? Nothing, what we just write. The anodic reaction plus cathodic reaction separately, I simply add them. So anodic is this, the nickel solid plus and this reaction Ag2 plus. So it is because 2 electrons are involved here. So to balance this, we have to write 2 Ag plus equals nickel 2 plus 2 Ag cell. And this we know, what we know, this half cell reaction will be nickel solid, and at this vertical line you can write arrow in this direction. This is the anodic reaction. The cathodic reaction will be what? Ag plus, and then one arrow at here at this vertical line Ag. And now this both the reactions would be balanced in terms of the electrons lost and gain both. So this reaction will what is nickel to giving Ni2 plus, and two electrons balance the net charge, it will be 2 electrons, and here it is Ag plus electron give Ag, and here only one electron is involved, so we have to multiply entire thing with 2 to balance, to keep the number of electrons lost is equal to the number of electrons gained. And so this is the net cell reaction, and the next equation for this equation we can also write for this reaction. The E cell is equal to E naught cell minus RT divided by NF, and N is what the number of electrons taking part into the reaction, and number of electrons is 2 electrons taking part in this reaction that we see here, because Ni2 plus is here. So 2 and F is the Faraday's constant, and ln and the concentration of the product, and this concentration is a solid, we can consider it as equals to unity, so we don't write this, because even if you write and it's multiply this number if it's 1, it is not going to affect this value. So this we do not write, and this concentration of Ag plus, and we know the stoichiometric coefficient we also take into the account, we stoichiometric coefficient while writing reaction coefficients or equilibrium constant. And so the since two Ag plus ions are involved, so concentration of Ag plus ions to the square that we have to consider here. And thus E cell we can calculate E cell as equal to E naught cell minus 0.0592 divided by 2 log Ni2 plus divided by Ag plus ion concentration, this. So this is one thing that we can do. Now what can we do for a general, any general reaction, which is this similar thing we have seen in the equilibrium, chemical equilibrium as well. AA plus BB gives CC plus DD. However, there we have not written or seen the involvement of electrons there, because that those reactions could be redox reactions or any other general equilibrium reactions or reversible reactions. Here we have seen only the redox reversible reactions, which are redox reactions, where the oxidation and reductions are happening simultaneously. And so for this reaction, what can we do? That we can write the reaction coefficients Q as concentration of the product C into the stoichiometric coefficients of C into concentration of product D into a stoichiometric coefficient of D divided by concentration of reactant A to the power stoichiometric coefficient of A, reactant A, into concentration of reactant B into a stoichiometric coefficient of reactant B. And so this is the value of this. This is how we get the equation for the reaction coefficients. And so we can also write the Nernst equation, and Nernst equation for we have to write here the final equation for this reaction as well, for this reaction. So we can write E cell is equal to E naught cell minus RT divided by NF, and here we have signed why NF, because we have written that it's for a general reaction. The N electrons are involved in this reaction. N electrons are involved in what? The N electrons are being lost by certain atom or certain element, and the same number of electrons are accepted by or the received by some other element or the atoms, or the not atoms, by the ions. So, but we get the E naught cell minus RT by NF ln, and then the value of Q we can write. The Q is what? C to the power C into D to the power D divided by concentration of A. This thing we can write the value of Q directly from here, and that you can see directly. And thus E cell is equal to E naught cell minus RT divided by NF ln Q. The same thing again we got the. Why I am writing that, keeping these things with a different way, we are putting same equation, because this equation is very important for us. We should remember. Now let us look into this question, and then I'll stop. So Q here is the reaction coefficients. So now the question is, represent the cell in which the following reaction takes place. So we have to represent this cell, and then we have to find out E cell as well, and calculate its E cell if E naught cell is 3.17 volt. So this is the net reaction. Magnesium solid, when it reacts with the 2 Ag plus 0.001 molar, its concentration of the Ag plus is 0.001 molar concentration. So its concentration is very low, that you can see here. And it gives Mg2 plus, and its concentration is 0.13 molar, and 2 Ag solid. So what we know, the cell notation from this reaction we can write. So cell notation is Mg, the vertical line Mg2 plus, because the oxidation we can write as the reaction at anode. Then the two double vertical line, parallel lines for the salt bridge to represent salt bridge. Then the electrolyte solution for the silver electrode, the Ag, the concentration, and then Ag electrode. And for this, we can write the Const equation: E shell is equal to E naught shell minus RT divided by what we see, the involvement of 2 electrons here. So the value of N will be 2 by F ln, then the product divided by reactant. And what is the product here? This is the product. This is product, concentration of product divided by concentration of reactant to the power 2. And thus you can get this E cell is equal to E naught cell, value of E naught cell that is given, already given. So we can write at 3.17 volt minus RT divided by F, and this log we can write because it is 2.303 when multiplied, it will be equal to 0.0592 divided by 2 log. Then this concentrations, putting these values and then solving entire thing, what you get, these values you can solve, then you will get E cell will be equal to 2.987 volt. And this is the answer. So this is the way we can solve such questions. And I think the time is over, and I'll stop here. And from the next class, we will see the cell conductance of cell and these things that we see, the Kohlera's law and other things from the next class.